For incompressible flow, there's a very interesting connection between the concept of stream functions and streamlines. Streamlines are the tangent lines of a flow, where the lines to which the flow is everywhere tangent to them. Stream functions are related to incompressible flow in particular, and so the streamlines are these green lines. The stream functions are the way that we express an incompressible flow, and that's when we say that the velocity is equal to the curl of a stream function. Now we can say this for any flow. This is a decomposition that's valid and may or may not be useful. But for incompressible flow, it's a particularly useful one because we have that the divergence of u equals 0 for incompressible flow, and we know that the divergence of any curl will be 0. And this is true for all choices of the vector stream function psi. So we can generally decompose our flow into a vector potential, into a stream function representation, but it's particularly powerful for our incompressible flows, where the stream function representation guarantees the incompressible constraint. Okay, for a more general flow, we'd also have some other terms, some gradient scalar term, and we'll learn about that in a short amount of time. So for an incompressible flow, a stream function completely describes the flow, and the stream function enforces incompressibility. How are these tied to stream lines? Well, let's come back to our streamlines, our green lines. Our streamlines, these are the lines where they are everywhere, where the flow is everywhere tangent to them. And for streamlines, we noted before, we're going to just note in 2D, the tangent relationship says that dx of the streamline divided by the velocity u is equal to dy of the streamline divided by the y component of the velocity v, and here we'll just consider 2D for simplicity. Now, this describes a parametric relationship for a line, so the line will be everywhere perpendicular to the u vectors, where the u vector is u x hat plus v y hat. What else can we learn from this? Let's take this relationship here and let's rearrange it. Dx over u equals dy over v. That's the same as v dx minus u dy is 0, where the dx and dy are along our stream line. Now, let u equal the curl of psi, our stream function. So now let's insert that definition of u vector for its v and y component. So it's u component, non-vector, so this is the x hat component. This is minus d psi dy, and a psi here for 2D. Psi here is in the z direction. It's phi z hat. So we can actually erase our vector bits over this because there's only one part of the stream function in 2D. So u is given by d psi dy, and then v is given by the other part of our cross product. The v component is given by d psi dx. All right. Now let's insert those in to our stream function relationship. So we have inserting each of these into the appropriate bits. So the u bit here goes over here, and the v bit here goes over here. And you can see there's a really interesting connection between the derivatives of the partials and the derivatives of our stream function. And in particular, we have that d psi dx dx, so this is the v bit here, minus the negative d psi dy d itself dy. So here's the u bit coming in here. That's all equal to 0. And then if we get a little clever with our calculus here, and do some calculus by crossing out differentials, we get the inference that d psi is 0 along our streamline. So our streamlines are actually lines of constant stream function. A streamline is a line along which the value of the stream function is a constant. This tells us that if we could make, for example, a visualization of our stream function for a flow, if we plot contours on that stream function, we will immediately see the stream lines of the flow, since the stream lines of the flow are those points where a stream function has a constant value. That's a powerful way of visualizing the streamlines in a flow, especially from a mathematical solution to a flow where you want to see what those streamlines would look like and whether they look like the streak lines that you might be seeing in, for example, an experimental setup where you're doing dye, smoke, or other passive tracers released into a steady flow.